So today I'm talking about the other side of the pie. And so basically there's this problem that building very high performance virtual machines for dynamic languages is hard. And the reason we know that, and the way we know this is Python, Ruby, Perl, the general set of dynamic languages, everybody considers them slow. And the only fast are the ones that huge companies spend millions of dollars investing in. The JavaScript, which have Google and Apple and Mozilla investing millions of dollars in them. And well, really that's just about the only one that's popular dynamic language that's generally considered even remotely performant. So the PyPy project was created about 9 years ago at this point to address this problem of this incredible discrepancy between where we know we can be with performance and where we are today with most VMs. We know the 80s was like a hotbed of research for dynamic languages. Researchers proved you can make Self and the other dynamic languages that were popular then very faster, and nothing about the research is inapplicable to Python and Ruby and everything else. It's just that we considered it so much engineering effort that it hasn't been applied to a lot of these languages. So the PyPy project was created basically to remedy that issue. And so, yeah, basically, we know it doesn't have to be this way. PyPy's primary project has been building this framework for implementing dynamic languages and then implementing Python on top of it. And so, basically, what I wanted to show off today is just how easy it is to take advantage of this framework and build your own dynamic language, whether it's a fresh language from scratch or a language that already exists that you just want to re-implement, and really show that it can be implemented quickly without a lot of sort of special work. And so how many people here have taken either ModComp or like programming languages or something like that? Nice, that's most of the room. So virtual machines, interpreters, they basically have a pretty standard architecture. You take your source code, you turn it into a sequence of tokens, you parse that and get a syntax tree, you turn it into an abstract syntax tree and maybe do some sort of semantic analysis. You create some bytecode and then you interpret it. And maybe you don't even create some bytecode. Maybe you just interpret the abstract syntax tree directly. This is a pretty standard architecture and it's considered simple. If you wanted to implement your own VM, sort of traditionally a slow VM, using this architecture, it would be a not tremendous task. This is sort of a well-known architecture. We know how to implement these. It's not a hard problem. The problem with the PyPy project is trying to address is how to take this simple construction of what a VM is and turn it into something very, very high performance. So let's go ahead and sort of build this thing. So all the source code of this with commits that basically correspond to individual steps of this process. The source code is all available there. You can check it out if you want to follow along. There's another similar example VM at bitbucket.org/pypy/ I forget, it's also like example VM or something. If you just go to /pypy, you'll see it in the list of repositories. But so the language that I decided to implement is a pretty minimal subset of JavaScript. It has variables, it has floats and bools, it has a set of basic arithmetic operations, and an if statement, a while statement, and a print statement. So it's a pretty simple language, but it's dynamically typed. The compiler has no knowledge of types, and it's loosely based on JavaScript. So the first step is to lexing and parsing. And the PyPy project contains a lot of helpers for doing lexing and parsing. So let me see if I can view. So zoom in. So one of the major helpers is a parser generator for a grammar. So this is a pretty simple grammar for our language, except for it's scrolled slightly off, so everything's cut off. But you can see we have the operators that have the add level of precedence are plus and minus. The multiplication level of precedence is multiplication and division. Comparison operators are equals, greater than or equal, less than or equal, greater than, less than, and not equal. Floats, which are really just integers right now. This doesn't actually recognize anything with a decimal point. There's a sequence of numbers. Names are sequences of letters and numbers that begin with either a letter or an underscore. The body of this is a sequence of statements. A statement is either an expression, an if statement, a while statement, or a print statement. And then we sort of have, because operations have different precedences, we have this chaining of a comparison is the lowest precedence item, followed by addition, multiplication, parentheses, and raw atoms, which are floats and names. So, and then we have assignment, which is names. A name is equal to an expression. So this is a pretty standard grammar in the EBNF format. So it's pretty standard. The next stage of building a compiler. So this will automate the parser generator will automatically be able to take this and turn this into a tree of really annoying syntax nodes. So the next statement we want to take, the next step we want to take is to turn this into an abstract syntax tree. So we look at the tests. We can see that so sort of the one semicolon becomes a block, which is a single statement, which is a float value, or 1 plus 1 becomes a binary operation plus of a 1 and a 1. Subtraction 2 is another binary operation. If we have multiple terms, we get subtraction of 1 time 1 minus the result of the multiplication. So it's a pretty standard abstract syntax tree, and the way we do this is basically whoops, wrong file. No, right file. We basically just have this transformer that takes the really annoying nodes that the parser generator spits out, and it turns them into these blocks and these statements. So you know, if what we're seeing at this level is an if, we treat it as an if node, while, print, etc. This is pretty much the most boring stage possible in writing a VM. I hate parsers with a passion. I regard parsers as really annoying things you have to write before you get to write fun things. I hate them. So this is a pretty terrible parser, actually. I've learned to write better ones since I wrote this one. I really hate parsers. And so the next thing is we want to create bytecode. So bytecode is basically pretend that we're going to be building a CPU and then invent our own set of instructions for it.
Alex?
Yes?
So how do you do the compound statements, sequencing statements? What is the abstract syntax tree that I can see? What is it? Is there a statement delimiter between two statements?
Yeah, this language uses semicolons.
Semicolon,
yeah.
So do you put semicolons as sequencing operator somewhere in the abstract syntax tree?
Yeah, well, if we look at the grammar, basically they're represented because a statement is an expression followed by a, so they're no longer there by the time we're at the AST.
So can I look at the AST for example? Just
yeah, so here's any of these are example ASTs. So 1 plus 1 is a block, which has.
I can go down.
Yeah, so a block contains a sequence of statements. Yeah. So the next step is creating this bytecode. So we have to invent our own bytecode, basically inventing our own CPU. Because this is a pretty high-level language, dynamic language, we don't want to write something as low as like MIPS or x86. We don't want to deal with raw integers and pointers in our bytecode. We want to have something a little higher level that has operations like add, which does the correct behavior. If we have floats, it does float addition. If our language had strings, it would do string addition. We want a very high-level bytecode because it's a lot easier to implement and reason about. So if we look at our, here's a pretty simple example of it. The a equals 3 gets turned into loading a constant value, storing it in the name, discarding the top, and then returning null since that has no return value. So basically the idea is values that are constant in this language, like floats, their value can't be changed. They get stored in a constant table. So every bytecode object has a sequence of constants associated. So the bytecode load const takes an index into this table and puts this value on the stack. Store name takes an index into a list of the names. So every time a name is seen, you record what it is in the compiler, and you then you just put that name in the byte, or that index into the bytecode. So if we scroll down to another example, more names. I don't think I have any examples with more names, unfortunately. This one's a little more clear. So for I equals 0, we take the constant, which is its 0 position, which is also the 0 value, and we store it in the variable I, which is the 0th position. And then load name simply loads the value at that index. So we have basically variables, we have a mapping of variables to their index, and then the interpreter only has to worry about dealing with the index and not variable's name. It's basically an efficiency thing. We could represent that as a hash table of I mapped to its value, but mapping a single index is a bit cheaper. And so in practice, this is basically just we basically just recursively visit every node. So to compile a block, we just compile every statement in it. To compile a statement, we compile the expression it has, and then discard the result, because when an expression is in a statement, that means nothing's done with it. Assignment simply becomes we compile the value on the right-hand side, and then we create a store for it. Arithmetic becomes we compile the left-hand side, we compile the right-hand side, and then we have a specific bytecode for each operation. Similarly, a float, you can see, becomes this load constant operation, and then we just create float const, checks to see if we've already emitted a float constant with the same value, and saves the index to save a bit of memory if we have the same constant multiple times. And so at this point, we basically have this bytecode for an individual example, and then we have to write an object model. Basically, we now have sort of the bytecode, which is how we manipulate these objects. We have to decide what the objects actually look like in memory and how they're treated. So this being a nice dynamically typed languages, everything is an object. There are no exceptions. Integers are objects, functions are objects. Obviously, a lot of that isn't exposed in the language, but this is a subset of JavaScript, so we're sort of sticking with that semantic. Basically, the way I found that I like to represent this is with something called an object space, which is basically this magical object which is responsible for dealing with every operation in the language. So it has operations like new float, which takes a raw float value, like a float value on your CPU, and turns it into a floating point object, or a new bool, which creates a Boolean object, stuff like that. And then it has operations like, say, subtract, which which basically just dispatch to the object. So basically, if you ever wanted to change the semantics of your language, this is like sort of the one concrete place to do so. And then we get something like the ability to define a float object, which is like a subclass of the very base of this type hierarchy, and it stores a float, and it knows how to convert itself to a string. It knows how to do subtraction, which is just subtraction just returns a new float, which is its float value subtracted from turning the other interpreter object into a float. So we have this sort of dichotomy of we have interpreter values, which are things like this W float object. We use the W prefix to indicate it's a wrapped object, so it's not a raw value. And then we have actual raw values, like if you were writing C and you had a float object, it's not even an object, it's just a thing on your CPU or in memory. So we sort of have this two levels of stuff. But so we have these nice objects, and then finally we have an interpreter, which has a frame, which is responsible for storing the stack, and then the sequence of locals. And it has boring operations like push, which pushes a value onto the stack, and pop, which takes a value off the stack. And then finally we have an interpreter, which with all these different methods. So load const takes the table and just returns. It just pushes onto the stack the constant at the index. Or a little more metaprogramming is necessary, but so we automatically create subtract and greater than or equal bytecodes from this. We basically metaprogram. They both have the same implementation. They both just dispatch to the object space. So scary metaprogramming. And so the result is we have this interpreter that we run this while loop, counts down, we see it prints 3.0, 2.0, 1.0, and 0.0. And we get this output. And if we were to expand this language, we would add more operations, we would add more types. But basically, we have this sort of core that's just totally extensible and is everything you would need if you run it to write your own bytecode virtual machine. The next step would be to turn this into RPython. PyPy, in the process of creating this framework with this parser generator and other bits, created this language RPython, which is a subset of Python, which is basically statically typed, implicitly though. So you don't have to write types. The compiler is responsible for figuring out the types. But you do have to write code that adheres to the rules. So you can't mix types in a given code path. Basically all the rules of programming in C or Java, except you don't have to write the types down explicitly. And then once you reach that point, there's basically helpers that basically automatically apply a just-in-time compiler that implement sort of the past 20 years of research in how to make dynamically typed languages fast onto your interpreter in, it's about 5 lines of code, I would say, to take your bytecode interpreter from sort of the completely standard average, mediocre speed-wise, to about as fast as any dynamically typed language is today. If you look at the second example at the bitbucket.org/pypy/example or something, it shows it has the further steps of turning it into RPython and showing the JIT off as well. So thanks to everyone for listening. Thank you, Professor Morthy. Thank you to everyone here. So, questions?
What editor are you using for your?
It's called Sublime Text 2. It's unfortunately not open source, but it is pretty awesome. I can use Vim, sort of. I know how to delete more than one line at a time with Vim now. It's very cool.
Oh, promise.
Yeah.
So your language is built on Python? This whole thing's built on Python?
It's written in Python, yeah.
And how does the language that you make with it compare to the speed of Python?
So basically, they're in theory totally independent. That is, the speed of the final language has nothing to do with the speed of Python. This language being so simple, I would expect it to be faster. But I haven't benchmarked this. This is so simple.
So when you translate it through PyPy, the VM that's out is actually just raw code, right? It's just
Yeah, you get a binary like you get for anything else. Yeah, here I can show an example. Translating is fun because it has pretty colors. So yeah. Okay, this is apparently not in a good state. Never do a live demo of compiling something. Yeah. But, yeah.
So what about parallelism? So running multiple threads or multiple processes, I guess, or?
So one of the things this translation toolchain gives you for free is a garbage collector. Unfortunately, right now, none of the garbage collectors are thread aware. That is, if you try to allocate from multiple threads concurrently, bad things happen. But in theory, you have access to C libraries from this environment, so you can call into P threads, and if you were very careful to never allocate memory with the garbage collector, you would be able to have parallelism. Armin Rigo, who's one of the PyPy developers, is working on a project to use software transactional memory to allow true parallelism, but it's not done yet. So for now, not really. Okay, well, thank you guys very much.